This is a circuit diagram for the quantum search. In the previous video, we said that if we start our search registry in a state where every qubit is in the zero state and then apply the Hadamard gate to every qubit of the search registry, then we place our search registry into a state of equal superposition that we denoted by letter E. Then we apply so-called Groover iteration about square root of n times in order to put our search registry into a new state that we denoted by psi s. And the property of this psi s state is such that if now we do measurement of qubits in the search registry, then with a very high probability, we are going to get binary representation of the index s that corresponds to the solution of the search problem. Just for completeness, let me write down below that we need to repeat Groover iterations about square root of n times, or a little bit more precisely, we need to repeat them about pi over 4 square root of n times. Now let's take a closer look at the Groover iteration in order to see why this whole procedure actually works. The Groover iteration consists of the four following parts. It consists of an oracle, a set of Hadamard gates, a phase shift operator, and a set of Hadamard gates. The oracle takes as an input search registry and qubits of the search registry, and it requires for implementation purposes at least one ancillary qubit, one additional qubit, which does not directly interact with the search registry, but it's needed to implement the oracle. The oracle can recognize the solution. It does not know the solution in advance, but if it sees the solution, then it changes the phase of the search registry from +1 to -1. So if the search registry in the state of S, it changes it to -S. If the search registry is in any other state, then it doesn't do anything to the search registry. So this is X not equal S, nothing happens. The ancillary qubit does not directly interact with the search registry, and for a lot of practical purposes, it is convenient to talk about oracle acting only on the search registry. So let's write the following. We will denote oracle as O, and O acting on the search registry states X in general can be written in the following form. It is equal to X if X is not equal S, and it is equal to minus vector X if X is a solution. So this is oracle. Let's talk about the phase shift operator. The phase shift operator does the following thing. If it sees the state of the search registry in the zero state, it doesn't do anything. So 0 goes to 0. But if it sees the search registry in any other state, it changes the phase of it from +1 to -1. So X goes to -X for any X that is not equal to 0. So we will denote phase shift operator as P. Then we can write P acting on the state X in the following form. It is equal to X if X is equal to 0. So it doesn't change the 0 state, but any other state will be changed to -6. So there is a phase shift for any state other than 0 if X is not equal to 0. So then we can write the matrix form for the Groover iteration. G is equal, and we will write it from right to left. This is how matrix is acting on a vector. So first we have oracle, followed by Hadamard gate, followed by phase shift operator, followed by Hadamard gate again. And because we have a set of Hadamard gates rather than a single Hadamard gate, we will write a Kronecker operator here. Let me do it a little bit more carefully. So Kronecker operator n here and here. And the role of this notation here, just to make sure that we are saying that this is not a single Hadamard gate, but rather a set of Hadamard gates. So the Hadamard gates is tensor with itself n times. And this is the general form of the Groover iteration. So Oracle, Hadamard gates, phase shift, Hadamard gates. That completes the Groover iteration. Let's take a look at the geometrical interpretation of the Groover iteration to see why, after applying this operation about square root of n times, we are getting very close to the solution. Let's write the matrix form of the Groover iteration. H, P, H, O, and we will break it down into two parts. This is going to be first part, just Oracle, and this combination HPH will be the second part. And we'll start from the first part. We can show that Oracle can be written in the following form as identity matrix I minus 2 times cat S bra S, where S is the solution. And we can verify that this is indeed a correct representation of Oracle. Let's first check Oracle acting on the solution vector S. It will be identity matrix I times vector S minus 2 cat S bra S vector S. And because S is a unit length vector, the scalar product to itself will be 1. And we can rewrite this expression as vector S minus 2 vector S times 1. And this is equal just minus S. So now let's check what happens when Oracle in this form acts on non-solution. X is now not a solution vector. And it will be identity matrix times X minus 2 cat S bra S and X. So this is scalar product of S to X. Those are different orthogonal vectors, so their scalar product is equal to 0. And therefore, here we have vector X minus 0, which is equal X. So we verify that this form of the Oracle indeed the correct one, because it doesn't do anything to a non-solution, and it changes the phase of a solution to the opposite, from +1 to -1. With that, we can introduce a two-dimensional basis consisting of a vector S, our solution vector, and we will introduce a vector K orthogonal to the vector S. And vector K is a superposition of all non-solution vectors. X not equal to S. And for normalization purposes, we have to write here a normalization factor of n minus 1, because we want to preserve the unit lengths of our basis vectors. So now let's consider an arbitrary vector psi. And if this angle is gamma, arbitrary angle, then we can write psi as cosine gamma k plus sine gamma s. And if we apply oracle to this arbitrary vector psi, we will not change the first part because k doesn't contain any solutions. And we will change the sign of the second part because s is a solution. And geometrically, what it means, since we're going from plus sine gamma to minus sine gamma, we are getting now this vector, which goes into the negative part of the S space. And this vector here is oracle psi, and it has the same angle. So what oracle does to an arbitrary vector, it reflects it with respect to the vector k, where k is a superposition of all non-solution vectors if you project everything in 2 dimensions. So in 2 dimensions, oracle just reflects arbitrary state psi with respect to the vector k. Before moving to the second part of the Gruber iteration that contains the phase shift operator, let's make a quick note here about reflections in general. And I'd like to build here on what we already know about the oracle operator. The oracle reflects an arbitrary vector psi about vector k. And let's assume that the reflection angle here is gamma. We can also view oracle as a 2-step process where we make first reflection about vector s. So we reflect vector psi about vector s. And then we add an additional necessary rotation to align this vector with O psi. Because we are making a reflection here, that means that these 2 angles are the same. And this angle here is equal pi over 2 minus gamma. This angle here is pi over 2 minus gamma as well. And this means that this angle is gamma. This is a right angle, pi over 2. And this angle here is pi over 2 minus gamma. Therefore, at this second step where we're making rotation, we are rotating at the following angle, going from left to right here. It's gamma plus pi over 2 plus pi over 2 minus gamma, which is all equal to pi. So the total rotation here is actually 180 degrees, and that means that this vector here is minus O psi. So this minus O operator is an operator that reflects an arbitrary vector psi around vector S. But we know that O, the oracle operator, is the identity matrix minus 2 cat S bra S. And therefore minus O will be, and we're going to change the order of the terms on the right hand side, will be 2 cat S bra S minus the identity matrix. So this part here is a reflection about vector S. But this is also true for any vector. So for any vector phi, we can write a reflection operator, let's call it R, in the following form: 2 cat phi bra phi minus the identity matrix. To illustrate it, let's draw a vector phi. And let's assume we have another vector, let's call it mu. And if this angle is alpha, in order to reflect vector mu about vector phi, we need to apply this reflection operator R to the vector mu. So then this is going to be a reflection. So in summary, this is the form of the reflection operator about vector phi. And we are going to use this fact in just about a moment when we're going to talk about the phase shift operator in the second part of the Groover iteration. Now we are ready to discuss the second part of the Groover iteration, which consists of the Hadamard gate, phase shift operator, and the Hadamard gate. So this is our second part, and the first part was just the oracle. And we will start from just operator P. And we will remember that phase shift operator doesn't change the phase of the zero state of the search registry, but it changes the phase of any other state from +1 to -1. As such, we will make an assumption that the phase shift operator is just a reflection about the zero state. And then we will verify if such assumption holds. So this is an expression for reflection about the zero state. And now let's see what happens when we act with P on vector 0. It will be 2, cat 0, bri 0, vector 0 minus identity matrix times 0 vector. This part here equal to 1 because this is the scalar product of a unit length vector to itself, and therefore this becomes 2, 0 minus 0 vector, and this is equal just the 0 vector. Now let's see what happens when we act with operator P on a vector x, where x is not equal to 0. We will get 2 cat 0 bri 0 x minus I x. This part here now equals to 0 because it's now a scalar product of two orthogonal vectors, and therefore this all becomes 0, just a number 0 here, minus the x vector, it will be minus x. So we can check both conditions for the phase shift operator. Acting on a 0 state, nothing happens. Acting on any other vector, phase changes from +1 to -1. Now let's remind ourselves that H acting on the 0 state is equal to the equal superposition state E. The same is true for the cat version of it. And I'm here a little bit ahead of myself. So let's write it properly. Cat 0H equal to cat E. And now we can put it all together and write expression for HPH using everything we know. So this will become 2 H cat 0 bri 0 H minus H identity matrix Hadamard gate. So now here, this part, so this part becomes E. This is also E, but cat version of it. And this is equal to H times H. But now let's remember that the Hadamard gate is an inverse of itself, and therefore H times H is equal to the identity matrix. And therefore HPH is now equal to 2 cat E bra E minus the identity matrix. But this is nothing else but the reflection about the vector E. So the second part of the Groover iteration is just a reflection about the equal superposition state. We established that Groover iteration consists of two reflections. The first reflection is about vector K, And the second reflection is about vector E. Two reflections results in one rotation. Therefore, we need to figure out what direction that rotation is and by what angle. To do that, we will trace down what is happening with an arbitrary vector psi when a single groovy iteration is applied to that vector. For convenience, we will denote this angle between vector E and vector K as delta over 2. And we will see why it is convenient to use factor 1 over 2 a little bit later. And we will mark this angle between psi and K as two-line angle. And we will assume that it's equal to gamma. When we apply the first step of the groovy iteration, the oracle, then we will rotate our vector psi about vector K, and we will get O psi vector, where this angle between K and O psi is also gamma. Now we need to do the second step and reflect vector O psi with respect to vector E. We need to reflect it at this angle, which we will mark with 3 lines. And this angle is equal to gamma plus delta over 2. So when we apply H, P, H to vector O psi, we get this new vector, which is actually a complete groovy iteration now, G psi. And since this is a reflection about vector E, then this angle between G psi and E is also can be marked with 3 lines, and it is equal also gamma plus delta over 2. But we are interested in this angle between G psi and psi. So this is the angle we'd like to find out. We know that this small angle here, which I will denote with dotted lines, is gamma minus delta over 2. And the angle in question, the angle between vector G psi and vector psi, is equal to this 3-line angle minus this dotted line angle. So let's schematically write it as 3-line angle minus dotted line angle. And we said that 3-line angle is gamma plus delta over 2. And this dotted line angle is gamma minus delta over 2, which is equal to delta. So I will rewrite it, redraw on a SK plane. We have vector E, which we said is at angle delta over 2 with respect to vector K. And now we have this arbitrary vector psi. And when we apply one groovy iteration to that vector psi, we get G psi. And this angle over here is equal to delta. So one groovy iteration rotates an arbitrary vector psi at angle which is 2 times larger than the angle between vector E and vector K. So the question, of course, is, do we know what is delta over 2? And the answer to this question is yes, and we will see that in a moment. To find out the value for angle delta over 2 or angle delta, we will use the definition of the equal superposition state. We will write that vector E is equal to the sum of all possible states of the search registry. So sum over all x from 0 to n minus 1. And because it's a unit vector, the normalization factor here is 1 over square root of n. Now we can take out one term that corresponds to the solution. So we'll write separately 1 square root of n ket s, and then the rest of the sum will be the sum of all non-solutions. So we will write all non-solutions. X is not equal to s, n minus 1 ket x. But we already used the sum of all non-solutions when we defined vector k. Vector k, by definition, was a unit vector that corresponds to all non-solutions. So the sum will be the same. X not equal to s, ket x, n minus 1. And the normalization factor here was 1 over square root of n minus 1, because vector k is itself is a unit vector. So now comparing these two expressions, we can write that vector e is equal to 1 over square root of n ket s plus square root of n minus 1 divided by square root of n ket k. But geometrically, we can also write that vector e is equal to sine delta over 2 ket s plus cosine delta over 2 ket k. So comparing these two, it's easy to see that sine of delta over 2 is equal to 1 over square root of n. And from here we get an exact expression for vector delta, which is equal to 2 arcsine of 1 over square root of n. For large n, when the search space is large, we can simplify it and write it in a more simple form. So let's do it. For n much greater than 1, delta becomes, with a very good approximation, 2 divided over square root of n. So this is an expression for the angle to which one Gruber iteration rotate an arbitrary vector. Now we can figure out how many times we need to apply Gruber iteration in order to solve the search problem. So we start at the equal superposition state E, which is at angle delta over 2 with respect to the k vector. And we apply one Gruber iteration here. And by doing that, we now know that we will rotate this vector E by angle delta. So this angle will be delta. We can apply one more. This will be 2 Gruber iterations applied to the vector E. And again, this angle will be delta. And we can keep doing that until we get very close to the vector S. So let's say that after multiple Gruber iterations, we end up here. So we applied it multiple times to vector E. And let's say this is M. So we would like to find out what M is equal to in order to get to the vector S as close as possible. So let's make this angle alpha. And since we get as close as possible, then we actually get to that state that we talked about earlier, that psi s, where the property of this psi s state is such that if it is measured, then there's a very high probability it will reveal the solution. So we'll write it in the following form. So the probability of measuring psi s that reveals S, and we're saying that because it's very close to the S, it is approaching 1. So it is very high probability. Now let's write an expression for vector psi S in terms of angle alpha. It will be equal to cosine alpha s plus sine alpha k. But then the probability of measuring s will be equal square of this amplitude. So this probability will be equal to cosine alpha squared. And we are saying that it should be approaching 1. Therefore, alpha, the angle, should be very small. Now let's write an expression for alpha. Alpha is equal to pi over 2 minus delta over 2. We're subtracting delta over 2 because this angle between vector E and K was delta over 2 to begin with. And now we applied m Grover iterations. So now we're saying that this angle here will be m delta. And now we need to solve this for m. So from here, m is equal to pi over 2 delta minus 1/2. And of course, we have to round this to the nearest integer because m has to be integer. So we'll write it as such, round. And now we will remember that delta is equal to 2 arcsine 1 over square root of n. And for large n, delta with a very good approximation is equal to 2 over square root of n. Therefore, for large n's, we will get m equal to approximately pi over 4 square root of n. And here we are neglecting this term 1 over 2. For large n, this is a fair approximation. And therefore, we have just proven that in order to solve search problem, we need to apply Grover iteration, and therefore we need to call oracle approximately square root of n times. This factor p over 4 is good to remember, but in general, the scaling as square root of n is now proven. Before wrapping up this video on quantum search, I'd like to discuss how close we can get to the solution by applying proper number of Grover iterations. Or what is the probability that at the end of the day, after we've done every step in the quantum search algorithm, we will not get the right solution, and what would we do after that? So we applied proper number of Grover iterations, rotated our vector E to the state psi s, and we'd like to know how small angle alpha could be. Here I wrote an expression for angle alpha, knowing everything that we discussed. So this is delta over 2. This part here is m, and this is delta. Let's first take a look at the special case when n is equal to 4. In this case, arcsine 1 over square root of n is equal to arcsine of 1/2, and this is equal to pi over 6. Putting that pi over 6 in our expression for alpha, we get pi over 2 minus pi over 6 minus round, and the expression for the Grover iteration number, pi over 4 divided by pi over 6 minus 1/2 times 2 times pi over 6. So when we put it all together, we get pi over 2 minus pi over 6 minus pi over 3, and this is equal 0. So this part here is equal to 1, and this is quite remarkable. We can find the solution to the search problem when n is equal 4, applying just 1 Grover iterations. or in other words, we will call oracle only once. While in the classically, classical search would require m on average equal to 2.25. But in quantum search, using just one oracle call, we can find the solution to the search problem. Now let's see what is the error on measurement when we use quantum search algorithm in a more general case when n is not equal to 4. Whenever we apply m Grover iterations, we will rotate our vector search registry within angle which is smaller than delta over 2. So alpha is always smaller than delta over 2, and therefore the probability that we will not measure a solution, in other words, the probability of measurement on vector psi s not resulting into a solution is the same as probability measuring psi s and getting k. But we know that psi s is equal to cosine alpha s plus sine alpha k, and therefore the probability of getting k is just sine alpha squared. So the probability of an error is equal to sine square alpha, and this is smaller than sine square delta over 2, and therefore in general for large n, probability of an error is smaller than 1 over n. So you can imagine that for large n, this probability is very small. For a search registry, when we use for search space, when n is equal 1 billion, the probability of an error is smaller than 10 to the minus 9. But it could happen. We may measure vector psi s, and we will not get a solution, which we will find out by checking the solution with Oracle. In that case, all we have to do is to repeat the whole quantum search algorithm again. So we go to the equal superposition state and apply m Grover iterations one more time. And again, the probability of an error not getting a solution will be 1 over n, extremely small number. So within a couple of applications of Grover algorithm altogether, quantum search algorithm, we are guaranteed to find the solution with very high probability. And in the case of n equal 4, we guaranteed to find it exactly with one iteration. So with that, I'd like to finish this video on the quantum search. We haven't discussed everything in the quantum search. There are a lot of interesting details on the implementation and how the oracle is being constructed. I hope to cover those details in the future videos. But for now, thank you very much for listening to this video. And I hope to see you in the next videos. Thank you.